Hey there, everybody. Welcome back. We're going to continue 13.2. This is on limits and continuity for multivariable functions. And we just got done talking about how it takes different paths. And the only real way to show that something that the limit exists is to do a delta epsilon proof. Many of you have not seen it in 2 dimensions, so I thought I'd better start there. So we're going to just start with this graph. Just focus on the graph y equals f of x right here. That's the red line. And what we're going to do is we're going to have some y values, the limit right there. And then we want to go a distance away from it up and down. And we're going to call that distance epsilon. That's the E. And we want to show that no matter how small epsilon gets, we can get it down to like that and like that. There is still a window on D, or there's still a window where we can find X values that will get us that. We can see that the X values are there, right there. It's really narrow. It's a little bit easier to see when it's wider. That value we call delta, the distance delta from the X value. Now you'll notice, like especially on this one, we can see that the widths are a little bit different. So like if I'm trying to, the limit is L when X gets to A. So as X approaches A, limit as X goes to A of f of X equals L. That's what we're looking at right now. We can see that depending on the graph, sometimes we want the vertical height to be the same for epsilon. The epsilon needs to be the same, but sometimes that makes a different width on the left down below. Like on the left side, it's wider between where the X value is, say X1 and A, as opposed to the right side, X2 and A. So we could call one, we're going to use delta for the distance from A to our X values that we're working on. And we want to choose the smaller one so that we're doing. So we want to show, the object is to show, no matter how small we make this epsilon window, we can show that there is a value less than the distance delta away from A that will produce a value in that f of X range. Okay. So I tried to explain that in like layman's terms on the right. We'll just take a look at it, the math lingo here. If f of X approaches L as X approaches A, then for any epsilon greater than 0, we can find an open interval, X1 to X2, that contains A. And has the property that for each X in that window, X1 to X2, except for maybe at X equals A. Remember the limit, it doesn't have to be continuous at A. The limit just has to be the same coming in from the left to right for 2 dimensions. So if we, for no matter what size epsilon we get from L, there is that window for X1 and X2 that we will have a value that'll get us, when we plug it into function f of X, we will get a value between L minus epsilon and L plus epsilon. So like anywhere along here, if I plug anything in here in this window between X1 and X2, my Y value is between L minus epsilon and L plus epsilon. I'm off the screen here. It's between wherever we plug in the X, whether it's here, whether it's here, the Y value is between L minus epsilon and L plus epsilon. That's what we need to do. So what does L minus, we have L minus epsilon is less than f of X, which is less than L plus epsilon. And for our X value, we have A minus delta is less than X, which is less than A plus delta. We can write that in terms of absolute values, where we have f of X minus L. We just subtract L from every region here. We have f of X minus L L is less than epsilon when it's going to be the absolute value. That's how we get the negative E over here. It addresses the negative E. It is going to be, since it's absolute value, it's not going to have a negative value, so it's greater than 0. And then we do the same thing with this one right here. We subtract A from all regions, and we have X minus A in the middle. We've got negative delta on the left, positive delta on the right. That condenses to the absolute value of X minus A is less than delta. Again, it's an absolute value, and we don't want the distance to be 0 because we're not actually checking at X equals A. Okay? We're not checking at X equals A, so we're not checking when f of X exactly equals L. That's not how limits work. Limits come in from both sides. Okay? So let's see what that means in terms of a proof. This kind of leads to our limit definition. Let f of X be defined for all X. That symbol there, the upside down A, means for all. Let f of X be defined for all X on some open interval containing X equals A, except for possibly at X equals A itself. Then the limit as X approaches A of f of X equals L is true if given any epsilon greater than 0. We can find a number delta that's greater than 0 such that 0 being less than the absolute value of X minus A is less than delta implies that arrow to the right means it implies or leads to f of the absolute value of f of X minus L is less than epsilon. We have to show that if we start with something with absolute value of X minus A less than delta, that we can get to f of X minus L is less than epsilon, which means we're going to look at forming some relationship between delta and epsilon, as you'll see here. This is, I know this is not the best description of it. This is my first time giving a delta epsilon explanation. But let's look at an example. We are going to prove that the limit as X approaches 3 of 4X minus 10 equals 2. So to do that, I'm plugging in stuff up here to get this. F of X was 4X minus 10. I'm putting it there and I got that. I plug in 2 right here for L. I got that. So this matches that. And then X minus A, X goes to 3, X goes to A. So we got X minus 3 here. So we need to show that if we start with 0 is less than the absolute value of X minus 3 is less than delta, we end up with 4X minus 10 minus 2 is less than epsilon. So again, we want to find delta in terms of an epsilon. It's usually easiest to start with working backwards. We're going to start with the f of X minus L is less than epsilon, find what we need, and we're going to say delta equals that value, as you'll see here. So the absolute value of 4X minus 10 minus 2, if I combine it, it's 4X minus 12. And I can factor out a 4. And since 4 is positive, absolute values where you have products, they multiply like that. 4 is positive. We can drop the absolute value sign on the 4 and divide it over. I now have X minus 3 in absolute value signs, and I have less than epsilon over 4. This matches what I have up here. Okay, so we're going to pick delta to equal epsilon over 4. So if we're looking at a width of 0.5 up or down from our limit, our delta needs to be 0.5 divided by 4, which is what, 0.1125 or 0.125. It needs to be a narrow window. So all we did is found the delta that we're going to use. We're going to write out the proof in a second. So this is just all work to find the proof. The general form of the proof is to prove the limit as X approaches A of f of X equals L. We're going to say let epsilon greater than 0 be given. There exists a delta greater than 0 such that for all X, 0 less than the absolute value of X minus A is less than delta, implies that f of x minus L is less than epsilon. Then that's how we start the proof. We will say what our definition of delta is, and then we will show, starting with x minus a is less than delta, we can lead to this. Okay, so for all, I told you this is the upside down a. There exists is the capital E that's backwards. You will see this in text also. So let's prove the limit as x approaches 3 of f of x equaling 4x minus 10 equals 2. So we prove the limit. We're going to say let epsilon greater than 0 be given. There exists a delta greater than 0 such that for all x, the expression 0 less than the absolute value of x minus 3 less than delta implies that the absolute value of 4x minus 10 minus 2 is less than epsilon. And we start working forward. We say define delta to equal epsilon over 4. And since epsilon was greater than 0, this shows us that delta is greater than 0. And then we start with 0 times is less than x minus 3, the absolute value, which is less than delta. We are going to replace delta with the epsilon over 4. And I dropped the 0 for now, just so we don't need to keep writing it. If I multiply both sides by 4, it gets epsilon by itself on the right. I've got 4 times the absolute value of x minus 3. I move the 4 inside. I've got 4x minus 12 is less than epsilon. And then I separate it out to look like f of x minus L. We want to put it in that form. Then they like to finish it off by saying, therefore, the limit as x approaches 3 of the f of x equaling 4x minus 10, the limit is 2. And they use QED. That's the letters to show that a proof is done. It stands for, I'm not going to say it right, quod erat demonstratum, which means which was to be demonstrated. We demonstrated that the limit as x approaches 3 of 4x minus 10 equals 2, regardless what epsilon we pick. That's it for the 2-dimensional version. We'll kick it up to the 3-dimensional in the next video. Peace.